Most of you probably don't know who Monica is, but just in case you wandered in, because this looked like an interesting meeting. So Monica came to Northwestern 4 2/3 years ago. Is that a pretty good estimate?
Yeah, that's pretty accurate.
Yeah, from UCLA. There was a UCLA mafia in the group for a while. Now Jason and Professor Farha are the last of the Mohicans in about an hour from now. So Monica came here as a Gates Millennium Scholar, and most of you know Monica is self-effacing. So she was here 3 years before I figured out that she was a Gates Millennium Scholar. She was an NSF fellow for about 30 seconds before declining the fellowship in favor of a National Defense Science and Engineering Graduate Fellowship. She took Huff's Rule number 31 to the next level, which most of you know, if you're graduate students in the group, is that if you want to get something done, hire yourself a couple of postdocs. So Monica had enough of postdocs only working 12 or 14 hours a day, and she hired herself 5 robots. So she's going to tell us today about a really ambitious project, the idea being, could you take MOF chemistry and build something that at least conceptually mimics the entire light harvesting system of photosynthesis, but do it with no proteins and do it in a way that lets you get a PhD in 4 2/3 years. So she's done some really interesting work. I think we're going to spend years building on it and expanding upon it, and she's going to tell us about some of it today. Monica?
Thank you, Joe, for that very flattering introduction. So today I'll be talking to you about my work on synthesis and characterization of metal-organic framework, or MOF, thin films, potentially that would be useful for solar energy applications. So let me give you a quick overview of my thesis. So essentially, Chapter 1 introduces the types of MOFs that are currently being used for photon collection as well as energy transfer. And specifically, in Chapter 2, my colleagues and I go into depth and study the photophysical phenomena of this porphyrin-based metal-organic framework single crystal. In Chapter 3, I expand upon that work and essentially deposit the porphyrin-based MOF into a thin film to study both light harvesting and energy transfer behavior. In Chapter 4, I expand upon this work and introduce apparently diamide-based linkers as light-absorbing components to expand light absorption of behavior. And in Chapter 5, I switch gears and essentially demonstrate that we are able to post-synthetically modify MOF thin films. But for the purposes of today, I'll only be going over my work in Chapter 3 as well as my work in Chapter 5. So currently, our global energy demand is on the order of 18 terawatts. And that's a number that's projected to increase up to 25 terawatts by the year 2035. And essentially, the estimate of global energy demand by the year 2050 is 30 terawatts. So this poses some very serious questions that we must answer. Namely, where will we actually obtain this energy to meet our future projected global energy demand? And secondly, how can we also try to tackle this problem by minimizing our fossil fuel resource use while maximizing our renewable energy resource use? So essentially, the amount of energy that we have can come from different types of renewable energy resources. And one of the most accessible ones actually comes from the sun. And essentially, about 96,000 terawatts of solar energy reaches the Earth's surface in 1 hour. So that's definitely enough energy to power the global economy by the year 2050. But more realistically, only about 29.2% of the Earth's surface is covered by land. And even making a more aggressive but more reasonable assumption, we can say that, let's say we cover only 2% of the Earth's land area with solar conversion modules. And just to give you a quick idea, that's about 1/3 of the United States land area. So that gives us about 560 terawatts of energy that you can harvest with this land area. Now, making the final reduction in the amount of energy that we can collect, let's say that we consider Shockley-Kaiser limit of about 32%, which is essentially the thermodynamic limit that stipulates how much of the sunlight can be converted to usable solar electricity. And assuming that the average conversion efficiency of commercial photovoltaic modules is about 12%, you could essentially harvest about 67 terawatts of energy from the sun per year. And let me remind you that that is definitely more than double the projected global energy demand by the year 2050. So essentially, the solar energy is a very feasible energy supply that we can use to fulfill our future energy demands. So let's also consider another factor, namely energy payback time for specifically organic photovoltaics or OPVs. An energy payback time is essentially the time required to generate the amount of energy that was used to actually make the energy conversion module. So out of all of these different types of energy conversion schemes, the organic photovoltaics has the shortest energy payback time. It comes out to about 12 days, whereas solar energy conversion schemes such as crystalline silicon modules take up to 19 months to generate the amount of energy that was used to actually make the actual module. So this means that OPVs definitely have better sustainability performance over all competing PV modules. So let's take a quick step back and talk about how organic photovoltaic works. So essentially, a photo-generated electron gets photoexcited and forms an electron-hole pair called an exciton. This exciton then splits at a donor-acceptor interface and then diffuses into separated charges upon application of a sufficient bias. And last but not least, the charges are collected at the respective electrodes, namely the electron at the cathode and the hole at the anode. But currently, there are still 4 main challenges that are hindering OPV performance. Namely, that there's very poor light harvesting using conventional organic linkers. There's inefficient exciton splitting into holes and electrons. Thirdly, there's problems with recombination of the separated charges. And last but not least, there's problems with collecting charges at the wrong interface, which might consequently form partial electrical shorting problems, for example. So what this tells us is the current OPVs that are constructed with conventional materials as well as conventional architectures are essentially not really simultaneously resolving these 4 challenges that I just mentioned here. So that gives us a reason to try to innovate different materials as well as novel architectures to tackle these 4 very serious challenges that are hindering OPV performance. So what can we consider? Yeah.
Monica, I haven't kept up in the last year or so, but what is, let's say, Yang at UCLA or Tobin here, or whoever the champion OPV team is, what is their very best right now? It's pretty good, isn't it?
The last OPV performance efficiency that I saw was like around 8%. I'm not sure if it has gone up even.
So before the topic of the answers to those, before perovskites, that would be pretty terrific.
Right.
Yeah.
Yes.
So Polera has close to 11 now.
Oh, I see. Okay. Right. So one potential material that I'm working on is what's called a metal organic framework, or MOF. And essentially, it's a self-assembling crystalline solid-state material that is composed of metal ions that are interconnected by organic linkers of moderate strength. And essentially, ligands are generally bound to the metal ions by a coordinate covalent bond. And examples of nodes include paddle wheel units, such as this paddle wheel unit that includes 2 zinc ions interconnected by 4 carboxylate linkers, as well as linkers, including this P1 dipyridyl porphyrin-based linker, and these 2 tetracarboxylate linkers, L1 and L2. So what this tells us is metal organic frameworks are readily treatable structures, since there's a spectrum of different organic linkers, as well as like inorganic nodes that can be used to assemble these materials. So one of the main challenges, as I had mentioned before, is that MOFs of current materials is that there's poor light harvesting. So one potential way that MOFs can tackle this problem is by essentially incorporating complementary absorbing linkers into MOFs so that we can potentially expand light absorption. And in one of our recent works in 2011, my colleagues had essentially combined this tetracarboxyl phenylporphyrin linker with zinc nitrate hexahydrate and DMF at 80 degrees Celsius, and then added this boron dipyromethane derivative that is dipyridyl, that's pyridine functionalized in a solution of an ethanolic solution with nitric acid at 80 degrees Celsius to form these plate-like black MOF crystals. And essentially, from the excitation spectrum, they saw that there were responsivity not only with a high molar extinction coefficient in the blue, and also to a lesser extent in the red regions, but also the low density was able to fill in the spectral gap in the green regions. So this tells us that MOFs can essentially be used to harvest most of the visible light spectrum. And another issue that is currently hindering OPV performance is that there's inefficient exciton splitting, mostly due to the limited diffusion length on the order of about 10 nanometers. And one way that MOFs can essentially try to tackle this problem is that we can exploit its precise arrangement of donor-acceptor chromophores and try to study and facilitate long-range energy transport. So my colleagues and I had essentially tried to assemble a DA MOF out of this dipyridyl-based porphyrin linker with this tetracarboxylate-based organic linker, as well as zinc nitrate hexahydrate and diethyl formamide at 100 degrees Celsius to form these zinc metallated porphyrin-based MOF. And essentially the DA MOF was formed, and it's a plate-like green crystal. Subsequently, we had doped the zinc metallated porphyrin with various concentrations of this quencher called ferrosinopyridine. And based on the observed fluorescence quenching, we saw that the average number of distinct struts that are visited within the 3 nanosecond lifetime of the DA MOF was equivalent to about 45 of these linkers, which is equivalent to about 25 hops. And this was very promising in terms of trying to extend the exciton diffusion length by a little bit more than 10 nanometers. Okay. Lastly, how do we tackle the challenges of recombination of separated charges as well as collecting charges at the wrong interface? So that is where I will introduce you to my work in chapter 3. So my hypothesis with this work was essentially by introducing MOF components stepwise, I would allow for us to form a MOF film, essentially the donor component of an OPV. And we can use this process and form a bilayer architecture, which can essentially minimize recombination effects as well as problems like electrical shorting in an OPV. So this essentially means I would need 2 things. 1, a MOF film, and 2, a technique for actually depositing these MOF components. So let me also introduce to you current techniques. So the traditional method of actually forming films involves solvent thermal growth. And this involves the mixing of inorganic precursors as well as organic linkers onto a pre-functionalized substrate in a high boiling solvent. And then baking this, or heating it at elevated temperatures for several days, and then forming a film of moth crystals. And what this technique allows is that it's very fast. You get very micron thick films, as well as pretty rough films. So even though this process gives you these advantages, it's very difficult to control the length scales with just solid thermal growth. And it's difficult to form films of desired thickness. So what I did was modify this method of film growth using layer by layer approach. And essentially this LPL growth is a stepwise approach that forms nanometer thick films and can potentially optimize optical path length and exciton propagation length within a moth film. And what this technique brings that wasn't brought before in traditional methods is that you can control the length scales very well with layer by layer deposition. Now let me introduce to you how this process actually works. So a pre-functionalized substrate, mainly a amine-terminated silicon substrate, recruits these zinc 2,4+ ions, and subsequently, to charge balance, these tetracarboxylate linkers are coordinated to the equatorial positions of the zinc paddle wheel units, followed by coordination of this dipyridyl porphyrin linker to the axial positions of the zinc 2,4+ paddle wheel units. And as a result of n number of cycles, you essentially get a film of homogeneous growth. So you can imagine that if I actually did this manually, it would take a very long time. So what I did to improve the efficiency of this process was to build a robot that Joe had mentioned earlier. And this is what it actually looks like in the lab. Schematically, if you break it down, this looks kind of complicated, but what I really need you to know is that the system allows for very good control of the immersion times of the pre-functionalized substrates. The reactant concentrations are very well controlled, as well as the temperature of the system is very precisely controlled. And because this is an automated technique, you get very good film reproducibility with this technique. So to do layer by layer growth, I used two different moth candidates, one of which was DA moth, because previously in our work, we had shown that there was very efficient exciton migration in this porphyrin-based moth. And secondly, the second candidate I chose was the L2 moth, which essentially includes the zinc 2,4+ ions, tetracarboxyl phenylporphyrin, as well as a dipyridyl linker that it acts as a spacer between the sheets of L2 porphyrin linkers. Let me note that the difference between these two moths is that the L2 linker, or the chromophoric linker in the L2 moth, is in the XY direction, while the P1 linker in the DA moth is oriented perpendicular to the substrate. So let me remind you that in my work, each cycle of growth is essentially defined by deposition of the metal precursor, followed by a tetracarboxylate organic linker, as well as a dipyridyl organic linker. And these three steps essentially comprise what is called one cycle. So to monitor the growth, I did profilometry and monitored the thickness of the film growth as a function of cycles. And notice that from about 10 cycles to 120 cycles, the film growth goes from about 26 nanometers to about 52 nanometers. And this corresponds to a film growth rate of about 0.24 nanometers per cycle. And this is actually very good because this corresponds to about 1 molecular layer of growth per cycle, which is exactly what we want. And secondly, notice that the roughness decreases from about 6 nanometers to 3 nanometers in this case. And that corresponds very well to about 2 to 1 structural repeat units that are oriented perpendicular to the silicon substrate in this case.
Did you say 0.24 nanometers per cycle?
You didn't mean that.
Yeah, that seems a lot smaller than normal.
Did you mean 2.4?
Oh, sorry, yeah, 2.4, yes, yes. Yes. All right, and another thought that I had for this project was that typically incorporation of free-base porphyrin linkers in bulk crystals is typically a very difficult task because the acidic conditions as well as high temperature conditions that are used typically spontaneously metallate the porphyrin linkers. And so I thought that using a much more mild reaction condition in layer by layer growth, this problem would be circumvented. And so I essentially formed MOFs of, or MOF films of L2 MOF. And what I saw were that 4 Q bands were retained. And this corresponds to a D2H symmetry, essentially a non-metallated porphyrin in the MOF film.
Monica, what's the absolute absorbance for the nice film?
These absolute units were, I think, around 0.5.
0.5 is right now?
Yes. Okay. And one thing that I also noticed was that the full width half max of just drop cast L2 porphyrin linkers was 4 times wider than that of the Sorey band full width half max of an LBL assembled MOF film. So this tells us essentially two things. One being that in the drop cast form of just the L2 linkers, there's much more electronic interaction and aggregation. And secondly, in just an LBL assembled film, you get very good chromophoric isolation. So this was a good demonstration of using LBL to form non-metallated porphyrin films. So to assess the orientation of these porphyrins within the thin film, I hypothesized that since our films contain these dipyridyl-based zinc metallated porphyrin, I could take advantage of the fact that there's a main transition dipole moment of this P1 linker along this dipyridyl axis. And I could essentially demonstrate their alignment in LBL assembled films using techniques such as polarized fluorescence spectroscopy. And the method essentially examines fluorescence as a function of excitation angles. And so ideally, when the transition dipole moment of this porphyrin is aligned parallel to the incoming laser light, you would see these large contrasts in fluorescence intensity. And indeed, that is what I saw in these DA-MOF films that are assembled through this technique. But just drop casting these P1 components on a silicon substrate, for example, doesn't cause as much variation in the fluorescence intensity as that of the LBL assembled film, mostly because the transition dipole moments in a drop cast film is all randomly oriented. So that is exactly what we would have expected.
Monica, my recollection is that you built these vertically for synthetic convenience, and that you really wanted to push up the light harvesting efficiency. You build them parallel. Did you ever try building them parallel with this component? With the dipyridyl? I mean, it's obvious to me how to build them vertically with a dipyridyl, but not so much horizontally.
You mean using
that component
in
the X and Y?
XY directions? No, I did not.
Do you think it's possible?
Yes, definitely. We could always. You mean like porphyrin units?
Yeah, we have the green units in the planes.
Yeah, of course.
Did you want to stay a few months and so keep going? I think I know the answer.
One related question was just what I'm thinking about is, despite what the cartoons are saying, clearly we've got lots of linkers on the surface. What's going on in that first layer or so with regard to, clearly if the organic horizontal linker, shall we say, changes its size, it's grabbing onto different spots. So what's going on with the set of
So in the
other
first,
molecules that are just sitting there?
so in the first couple layers, I guess like between 0 to 10 cycles of film growth, by SEM I see just regions of nucleation. But after that, this film growth merges into a film growth region. So after that, I see that more homogeneous film growth is occurring on the surface.
So that disorder does not propagate.
Right.
What about, maybe you're going to tell us about this, but you did some PXRD or similar experiments, and
Right.
my recollection is that you don't immediately see order, and maybe not just because of signal to noise, but it takes a while to get.
Right. For very thin films, there is very minimal crystallinity, but it's there. I think we need to increase the number of cycles I need to deposit to.
So the thicker you make them, the more crystalline they become.
Right. Right. So in my group's previous study, since we observed that in a DA moth, we could see very efficient exciton migration, I reasoned that if I did this in a thin film, I should also be able to see similar phenomena. So what I did was assemble a DA moth film using layer by layer growth and deposited this far red absorbing S1 dye on the periphery of the DA moth film. And I chose this candidate because the S1 absorption overlaps very well with the P1 emission. So this sets up for one criteria for long-range Forster energy transfer. And so in a 50-cycle LBL film, I would expect that if multi-step energy transfer were very sufficiently rapid and efficient, then the emission from this DA moth film would decrease while the S1 emission of the red absorbing dye would increase. And indeed, that's what I see when I deposit S1 dye onto the periphery of the DA moth film. And furthermore, in the excitation spectra, I see that there are peaks at around 458 and 750, which are indicative of participation from both P1 as well as S1 when monitoring at the S1 emission. So both are participating light harvesters for S1 emission. So in summary, what I've shown is that we have formed oriented porous porphyrin-based thin films of DA moth and L2 moth using this LBL technique. And layer by layer is definitely a direct route to forming non-metallated porphyrin-based films. And thirdly, and most importantly, we observe complete energy transfer from the moth film to the far red absorbing red dye. And these are important findings for especially light harvesting and efficient energy transport behavior in for solar energy conversion devices. So switching gears, now I will talk about what I did in chapter 5 of my work. So basically one of the current challenges in moth research is that we need to develop methods that can form moths that are typically inaccessible by conventional solid thermal growth methods. And for example, the formation of this methyl-free analog of ZIP-8 is typically not possible from conventional solid thermal synthesis techniques. Secondly, incorporation of free-base porphyrins into this moth is also very difficult because, as I mentioned previously, these porphyrin linkers spontaneously metallate under these high temperature as well as acidic conditions. And so this precludes the formation of free-base porphyrins in moths. Okay, so a promising partial solution to the aforementioned problems is what's called post-synthesis modification, or PSM. And this is essentially a chemical alteration of the framework without changing the parent topology. And typically, in both of these examples, a second PSM step is necessary to introduce catalytic metal sites into the MOF that are typically incompatible with de novo MOF synthesis. And closely related to PSM is what's called the solvent-assisted linker exchange, or SALE. And SALE essentially works by exposing the parent MOF with excess amounts of replacement daughter linker. And this occurs by ligand exchange and not so much dissolution and recrystallization of the MOF. And consequently, the topology of the daughter MOF is, the topology of the parent MOF is retained. And so SALE has definitely been pioneered by Burnett and his coworkers, as well as our group, on specifically these pillared paddle wheel MOF systems. And let me also remind you that I previously also reported the synthesis of this L2 MOF film using this layer by layer technique. And this technique essentially forms a L2 MOF material containing sheets of this tetracarboxyl phenylporphyrin sheets that are pillared by these bipyridine linkers. And using this LVL growth, we get very good control of film thickness with molecular layer precision. So my hypothesis for this work was that given that PSM and both SALE enable the formation of difficult to synthesize MOFs as bulk materials, I reasoned that if I applied this technique to thin films, then I should also get similar results. And what I have shown here, what I've shown here is that essentially by using SALE, I would form the SALEF1 film from this parent L2 MOF film, and by doing post-metallation, I can form this magnesiated L2 MOF film. And bringing this back to the original challenges, by essentially modifying pre-assembled MOF films with various linkers, I can potentially expand light absorption or even elongate exciton lifetimes if we want to use these techniques to modify MOF films in the future. So as a candidate linker for exchange and replacement of the bipyridine linker, I chose this 1,4-diazobicyclooctane pillaring component, mostly for two reasons. One of them being that there's a difference in length between the bipyridine and the DABCO unit by more than 4 angstroms. And secondly, there's a difference in pKa of the conjugate acid. And in our previous works, we have noted that if the pKa of the conjugate acid of the pillar being replaced is, if the pK unit of the conjugate acid that is replacing the parent linker varies by more than pK unit of 2 units, then SALE essentially goes to completion. So by picking DABCO as a candidate for SALE, I hypothesized that SALE should also go to completion as well in a thin film form. Okay. So let's move ahead. All right. So typically for bulk samples of MOFs, we use proton NMR to monitor the progress of SALE. And the material quantities that are available in the thin film sample is much lower than that is detectable by NMR. And so I had to go around that and try to figure out what other techniques can be used to monitor the progress of SALE. And so I came up with using TOFSIMS, or time-of-flight secondary ion spectrometry. And this technique can be used to monitor the progress of SALE because it relies upon a primary ion beam that bombards the surface of the sample and ejects these fragments or secondary species that are detected by the mass spectrometer. And the main advantage of this technique is that the sensitivity goes down to 1 ppm and its resolution goes up to 9,000. Okay. So with TOFSIMS, I collected spectra of an LVL brome film, And in the case where there is no sale, I expected that this bipyridine linker would fragment into this pyridinium ion A, as well as this 1,3-cyclopentadienium species B. And indeed, without treatment of sale, I had only seen these fragments A and B. But after 13 hours of sale, I would only see fragments of the DAPCO, which would fragment into this methaniminium, and this ethane species D. And essentially that is what I see in the spectra after sale.
Monica, what is it that's doing the fragmenting? It's a
It's like a
beam of something.
Gallium primary ion beam. Yeah.
You're throwing bowling balls at these
Right.
balsa wood things.
Yes.
And how long does it take to etch through a film? Or maybe you're going to say something about that.
It depends on the.
There's a lot of vacuum in these. That's
Yeah,
pretty
yeah.
quick to
So
etch through.
I think it depends on like the film composition, whether it's like organic or inorganic. But in this case, it takes about, I think, close to like a minute and a half to etch through the entire film because it's very, very thin.
So if you had compositional modulation, could you get anything useful out of depth profiling?
Yes, you could. Yeah, you can monitor whether there are appearance of different species in the film as a function of depth. And you could also do this with XPS depth profiling as well. Okay. So I also figured that if the layer by layer grown films are indeed oriented as indicated in this cartoon here, complete exchange of the BIP pillars for DAPCO pillars should decrease the film thickness. So by using profilometry, I expected that the change in thickness should be about 15 nanometers, which would correspond to a complete exchange of the bipyridine linkers for DAPCO. And indeed, that is what I saw in this case. So this corroborated what I found in the Thompson's data. So moving forward, since I had seen success with sale, I also wanted to try post-synthesis modifications such as linker post-magnesiation. And what I essentially did in this case was, in using an L2 moth film, I reacted it with magnesium dibromide diethylbutyrate in dichloromethane for 12 hours and at room temperature, and essentially formed a magnesiated L2 moth film. But to actually check this, I did measurements such as UV-Vis absorption spectroscopy. And what this showed me was that the pattern of the Q bands came out to 2, which corresponded with a D4H symmetry, and that told me that there was indeed some sort of metallated porphyrin in the LBL film. And that was a great change after 12 hours of magnesiation. Whereas without any magnesiation occurring, I only saw 4 Q bands, which again corresponds to a D2H symmetry for a free-base porphyrin. But this only tells us that there's metallation in the moth film, but doesn't tell us the identity of the actual metal components. So
Looks like it's zinc from the diagram.
yes, that is.
Actually, it
what
also
I-
looks like the serrated didn't shift. You know, it shifts when you put the metal in the middle.
Maybe it's not very clear in this case. But in any case, I just wanted to have a quick check of whether there was metallation that occurred, but I wasn't sure what kind of metal content was in the film. So I had to do XPS, and in this case, I expected there to be a 2-to-1 ratio of zinc to magnesium ions in the moth film. And so after integrating the peaks, I noted that there was indeed a 2-to-1 zinc to magnesium ratio in a post-magnesiated MOF film. And also, since I was inspired by the success of this post-synthesis magnesiation reaction, I also wondered if the synthetic conditions would affect the actual magnesiation of the porphyrins in the MOFs. So previously, we had seen that in just normal bulk MOF crystals, there was only a retention of about 2% of the magnesium in previously magnesiated tetracarbonyl by ICP. So I wondered if we could retain all of the magnesiated porphyrins by using layer by layer synthesis, because essentially using soluble thermal synthesis, there's the acidic residue as well as the high temperature would spontaneously metallate the porphyrin linkers. But using this layer by layer assembly, there's very adequate rinsing after each step to remove any acidic residue that might be formed from the acetic acids from like the zinc acetate metal precursors that are used.
So just to be clear, sorry to interrupt, but at the top, when you say 98% is lost, you're also replacing the magnesium with zinc, or are you getting free base?
I think
You're cooking it in a fairly concentrated zinc nitrate solution.
Replacement of zinc for magnesium.
Yeah.
So the magnesiums are very weakly bound.
Yeah.
And so I wondered if I could actually retain the weakly bound magnesium 2+ ions in the porphyrin core after LBL synthesis. So again, I checked UV vis spectroscopy, and this also indicated that there was retention of the metallation. But to check the metal identity, again, I checked XPS, and I expected, again, a 2-to-1 ratio of zinc to magnesium, and indeed that is what I observed in the XPS spectra. So this was also a very promising result. So in summary, what I have shown you guys is that layer by layer assembled thin films of L2 MOF is a very robust platform that can be used for reactions such as SALE as well as PSM. And BIPI can be readily replaced by DAPCO as pillars in a SALE reaction. Furthermore, complete post-assembly metallation of 3-base porphyrins is also possible, even with weakly coordinating magnesium 2+ ions. And last but not least, using much milder LBL conditions, the weakly bound magnesium 2+ ions can also be fully retained during film assembly. And this was not observed in conventional soluble thermal synthesis conditions. So overall, the broad picture of my work in chapter 3 demonstrated that porphyrin-based MOFs can essentially be utilized for light harvesting as well as energy transfer. This layer-by-layer growth technique can integrate MOFs into thin films. And in chapter 5, I demonstrated that we can post-synthetically modify these MOF thin films, which could be essentially useful techniques to modify existing MOF templates for OPV applications. So that essentially concludes my talk. I would like to thank many people who are very important throughout my PhD career, and without them I would probably have floundered in grad school. And so I'd like to thank my advisors Joe and Omar, as well as everyone who has ever been on my thesis committee, Mike, Justin, Mike Pelton, and Franz, as well as my collaborators, Gary, David, Shenyi, Joe, Monlok, Mike Katz, Shinya, Pavlos, Hojin, Shinchi, Randy, as well as theorists, Samir, Diego, and people in my lab, Wojtek, another theorist, Suleiman at Harvard, as well as Idon and my undergrad mentee, Rohan. And also, I'd like to thank my family as well as all my friends in grad school. Without you guys, I think I would have also been too stressed out in grad school, so thank you guys for your advice and friendship and your support throughout the years. I really much appreciate the people who are attending today. And that pretty much concludes my talk. So I'd like to open the floor to any questions you might have.
I'd like to think of your robot as a 3D printer because it's such a hot topic. So, okay, so it's very cool. But for real, you showed that you could layer non-metallated porphyrins, right, and build it up that way. Do you think you can incorporate a metallation step inside of this system such that you could build a couple of layers of non-metallated porphyrins, metallate it, then build a couple more layers of non-metallated porphyrins, and metallate it with something else?
So you mean like forming zones of like free base porphyrins and then metallated porphyrins? And then...
Well, not necessarily free. Like start with free base porphyrins.
Uh-huh.
Have a step that involves metallating with whatever metallating reagent that you want. Wash it out. Build a few more layers of free base porphyrins. Metallate those with something else, and then continue this in order to generate blocks of differentially metallated porphyrins.
Yeah, I think potentially for if I wanted to magnesiate the porphyrins, I would be able to using the conditions that I had previously used. So essentially it's like combining like the parts of the chapter 5 work that I had shown.
Yeah, essentially.
Yeah, right. So yes, I could do that. Or more simply, I could just deposit previously magnesiated.
Well, that's not very elegant, now is it?
Sure.
I mean, well, to follow up on the question, would you be able to metallate specific zones? It seems to me your metallation process, is a full exchange of the system.
Right, so
You would have to be diffusion limited or something.
right, so that's why I think that depositing pre-magnesiated porphyrins would allow for better control for formation of zones that only contain magnesium and those that don't have them. So that would be more clear, and I could check that with like XPS stuff profiling or like OPSIMS profiling to see if there are exactly zones with magnesium and those without.
So I'm not in the field of MOFs, so there are some things that are not entirely obvious to me. But with this layer growth technique, I'm curious, what are the limits of sort of what is the thinnest layer that's still useful, since earlier it was brought up that these stars kind of like islands, right, on the substrate. So what's the sort of thinnest layer you can grow that's still useful, and what's the like largest layer or the thickness by which it becomes maybe more useful to grow by the normal methods and then like cut, if that's possible? Like, I don't know if it's possible to grow a moth and just cut it in half to get the length that the sort of layer that you want.
You mean cut it in half laterally? Or?
Sure, yeah. I mean, like, since this is some kind of crystal, does it have like shearing planes in the same idea that like a regular crystal would, so you could just cut it on some plane and then get what you want? And with that sort of technique, is there like a thickness and an upper limit to what you can grow by this technique? Is like 300 nanometers too thick? It'll take too long?
Yeah, so the one limitation of layer by layer growth is that it's a very slow process, which is typically why I don't grow like 300 cycles. That would take probably more than a week to do.
Okay.
So for the purposes of my measurements and experiments, like at least like 10 to 15 cycles of growth is needed to do very simple like UV vis absorption measurements, thickness measurements, just to check to see like what's actually deposited on the surface. I could like, conceptually I could definitely grow up to like 300 cycles of film, but that just would take a very long time, and I haven't thought of something that I would need to do with that yet. So.
I think Ben Clark, building on what you did, assayed films by electrochemistry, and he found if you need 4 or 5 layers in order to very effectively block something block a molecular species from sampling not finding any pinholes. I don't know if that answers your question. I think it really will come down to the
Yeah.
application.
Yeah,
If it's
right.
catalysis, one layer would be enough. The catalyst is not enough.
In terms of monitoring cell conversion through mass spectrometry, do you know if it's known or possible to do so with like mass spectrometry, in the sense that say you're exchanging two different linkers that are fragmenting similarly, such that you won't be necessarily very easily able to tell that you have done the full exchange. But let's say you were using those type of linkers that fragment similarly, could you do so? Because MALDI, the way it works is you use like an external matrix so it doesn't fragment. And so is that something that is known that you can use MALDI to do that monitoring?
I think it would depend on the sensitivity and the resolution of the. Are you talking about MALDI-TOF?
Yeah, MALDI.
Yeah, I would. I'm not sure what the sensitivity and resolution of that instrument is, but I would. have to
Probably
look at
similar
that. Okay.
to that.
Then in that case, I would have to grow the films on whatever template that you use to inject the sample into the MALDI-TOF.
Okay.
I'm not sure what surface. I guess it would be limited by the type of surface that you use for sampling in a MALDI-TOF. But you could potentially grow films on, I guess, a MALDI-TOF surface.
Yeah, I was just wondering, like, well, I mean, it's not really much of what you have to do, but just out of curiosity, whether those matrices that you use for MALDI would be like compatible with a MALDI, such that you can make that assessment.
Are the surfaces like, are they gold terminated or hydroxyl terminated?
I guess it can depend. It can be gold and like gold sulfur bond or something else.
Then I would say you should be able to conceptually, yeah.
I think that what you took advantage of was that the TOF SIMS instrument inherently has this etching capability with the gallium ions as well as rastering. The other forms of mass spectrometry, unless someone's designed them to interrogate surfaces, you're going to really know what you're sampling. You're sampling whatever flies instead of whatever it is that you're knocking off the film. And since you know what you're looking for, the severe fragmentation I don't think is a big deal.
Any other questions? Yeah.
So at the beginning you were talking about organic photovoltaics and how, for example, these LBL simply could help in, like, for example, to control the morphology of an active layer. But I was wondering if anyone has ever done that with moms, like using it for photovoltaic applications.
Not yet, like actually making a device out of it? No, not yet. That's for 2 or 3 more PhD theses, I would say.
There might be some unpublished work that someone in the room reviewed that was pretty impressive, but I can't say that.
Yeah, you're talking about the 2 papers that.
I would never discuss a paper with someone working on a PhD at the same area, but if I had, yeah, it might be those 2. I saw another question over here.
That was my question also about OPD.
To find I have one. This is silly. You brought it up. So if you cover a third of the U.S., it turns out that's about 15 quadrillion square centimeters. 10 to the 15 this little pieces. Do you think we'll ever get to a point where we're like, yeah, we can make 15 quadrillion centimeters of some solar cell material?
Do I think it's possible?
Yeah, I mean that would, if it cost 10 cents a centimeter, square centimeter, it would only be all of the money in the world ever.
I mean, it comes down to like the cost of manufacturing manufacturing.
Exactly, just
modules,
ignore
right?
this. Tell them it's an engineering problem.
And as the
Kind of
engineer in the room,
Yes.
there's probably that number of square centimeters produced per year of things like polyethylene film.
Yeah, I mean,
So-
you need to go into maybe roll to roll.
I asked her a question. She's doing basic research.
Monica, brings to mind a sunshot proposal you helped me write maybe in your first or second year, where we had some intimidating looking linker from the perspective of synthesis, and the argument was, well, if we got a femtogram of it, we could cover a square mile.
Yes.
Not quite, but these are awfully thin. There's not very many moles in a lot of the unit area.
So you ended up, if you have a kilo of this orphan, you'll do a lot. So you'll be fine.
Great.
Strem solved the problem.
Are there other questions for Monica before we go to closed questions?